Welcome my friends, welcome to my next lecture. So in my last lecture I talked about like notions of, again I just recall the notions of surfaces and smooth surfaces. Well, my plan is to talk about the what is called Stokes theorem and Gauss divergence theorem, because this is the last concept of this what is called courses. This course that means I have given kind of series of lectures. So this is the last concept in this course, so which is like Gauss divergence theorem and Stokes theorem. So in my last lecture I talked about like notions of surfaces, smooth surfaces. So now of course I talked about what is called like what is the unit normal vector. If I have a smooth surfaces, how do you calculate, what will be the unit normal? So now once I have the notions of surfaces, smooth surfaces and notions of what is called unit normal vector, you can calculate it. Now once I have that one, then I can talk about what is called oriented surfaces. Now so that's the part I will start with today. So oriented surface, and once I have done with the orientations of surfaces or oriented surfaces, then you will see once I have a oriented surface, then it will induce orientations in its boundary. So once I have that notions, then I think I am in a position to talk about or to make a statement of Stokes theorem, and couple of examples I will talk about. So that's the today's plan. I'll start with the notions of oriented surfaces, and I will make the statement of Stokes theorem, and couple of examples I will talk. So that's today's plan. Okay, so as I said in my last lecture, I talked about surfaces, smooth surfaces and the unit normal vector. So now let me start with the notions of what is called oriented surfaces, and once I have oriented surfaces, it will induce orientations, as I said, orientation to its boundary curve. Okay, so what is that? Okay, so that's the kind of title I have written. So oriented surface. What is oriented surface? Like this, I think if you remember, this kind of notions I already talked about when I talked about, I think, divergence, curl and surfaces, vector line integral. So surface integral when I talked about, I think maybe I have discussed those kind of notions. Anyway, I just recall it once again. So it says that, so a smooth surface can be oriented by its normal. So I have discussed about the what is called smooth surface. Also I already discussed about how to calculate the unit normal. Now once I have a smooth surface and the unit normal, then I can talk about oriented surface. What is that? Look, for a given surface S, we have two collections. What are the collections? Number one, you make a pair with surface S comma plus of n cap. So that means I am talking about a smooth surface along with plus, means I am talking about the normal which pointing outward. Okay, so outward normal, so that's called positive plus n cap. So that means surface S with positive normals plus n cap, that means normal pointing outward. Okay, so outward directions. Another pair I am considering that surface along with minus of n cap. Minus means you can easily guess. So if plus n cap, if it's like pointing outward, so minus n cap, that means in pointing downward, no? So therefore this one. So if I have a pair with a surface S with minus of n cap, then this surface S with negative normals, right? So that means it is pointing downward. Okay, so that's I'm normal pointing inward or downward, whatever it is. So if I have these two pairs, then I will say that the S comma plus n cap, it is actually orientation where the normal pointing upward, and if I take a pair with a smooth surface along with minus n cap, that means I am talking about my surface with orientation or means normal pointing what is called inward. Okay, now we always take the pair S comma plus n cap, and in this case we say that the surface is oriented positively. So in that means if I start with a smooth surface with plus of n cap, then I am talking about my surface is what is called oriented positively or positively oriented. That kind of things I will use. In fact, if I say that okay, you have a surface with some orientations, by default if I do not kind of give any kind of orientations, whether it is plus n cap or minus n cap, by default you assume that I am talking about a surface which is positively oriented. Okay. So therefore we always take the pair S comma plus n cap, and in this case we say that the surface S is positively oriented. So if the orientations of surfaces is not mentioned, it's suppose in some example or in some exercise, you assume that it is actually I am talking about the surfaces which is positively oriented. Now look, so this is the picture I try to draw a picture. So that means suppose this is my surfaces. Okay, so this is the, you see this is pointing upward. So that means I am talking about the surfaces positively oriented, and if the kind of at a point if the corresponding normal what is called pointing inward, that means I am talking about what is called negatively oriented. So this is like positively oriented. So this is, you can say that this is positively oriented and this is actually negatively oriented. Okay. So that means if I have a smooth surface and if I just denote whether I am talking about plus n cap or minus n cap, it depends on I am talking about the positively orientation or negatively orientation kind of thing. Okay. Okay, then you can think of, as I said, so once I have a like smooth surfaces which has some orientations, okay, and that oriented surface will induce our orientations in the boundary curve. So that's exactly I've written orientations of the boundary curves of oriented surfaces. So if I start with the oriented surfaces, then it will induce our orientations in the boundary curve. And what is that? Well, I have written. So we know that a surface S is said to be closed if it has no boundary points, that we know. So a surface is called closed if it has no boundary points. Now what I will do, I will start with a surface which is not closed, that means it has boundary points. That means you start with a surface and it has a boundary points, and if I collect all the boundary points, the set of all boundary points, it forms a simple closed curves. So if I start with a surface S which is not closed, and if I collect all the boundary points, it will become a simple closed curve. Okay. So that means you start with a smooth surface which is not closed, that means the collection of all boundary points gives a simple closed curve. Then once I start with the orientations of a, suppose you have start with a what is called some smooth surfaces with some orientation, say let it be positively oriented. Okay. Then we can define an orientations on the boundary. So that means if I start with a surface which is a positively oriented, that positively oriented surface will induce a orientation in the boundary. How do you do that? So we can define orientations on the boundary. This is the notations of boundary of this surface. So this is the kind of green one I have explained. See, look what I said, if we walk along the boundary curve del S in the directions, what directions? So our head points positive normal to S. So that means I will go through the what is called the boundary curve, and my towards my head, so in the directions of head, the normal is pointing, that means outward I am talking about. So that means in the directions of my head, the normal is pointing. So that's what exactly written. Our head points positive normal. Positive normal means I am talking about at each point the normal pointing upward, that means in the directions of my head. So that the surfaces should be to our left. So that means I should go in the boundary so that the normal pointing towards my head, and if I go in such a directions and if I see that in the left hand side my surfaces is there, so that the surfaces should be our left, such orientations of the boundary curve del S is called the positive orientations of the boundary curve, which is induced by the orientations of my surfaces S. Right. So therefore, if I start with a oriented surface, that means suppose you have a positively oriented surface, and I will move in my boundary curve of my surfaces in such a way so that the normal pointing outward, which is in the directions of my head, and if I go in that way so that in the left hand side my surfaces is there, so that I am talking about the positive directions of my boundary induced from the surfaces S. That's exactly I have written. So you see, such orientations of the boundary is called the positive orientation. So positive orientation means what? I have a smooth surfaces, I have orientations, so I will go in my boundary in such a way so that in the left hand side I will have the surfaces, and of course I will go in such a so that the normal, the given normal in the oriented surface which is pointing outward or in one pointing towards my head. Like if this is the things happen, then I am talking about it's a positive orientation. And if the surface is on the right, then I will say that it is a negative orientation of my boundary curve. Now these two pictures I have given, this exactly it says that. Look, so first of all I start with a surfaces S, so it's like normal pointing upward, that means I am starting with a positively oriented smooth surfaces. Now look, the second one, you see I am moving in the directions in such a way so that normal pointing towards my head. So that means you see this is the direction and this is my head, right? So it means toward in the directions, and if I move in these directions, you see in the left hand side I will have this surface in the left hand side, I have surfaces in the left hand side. So that means this kind of orientation is called the positive orientations of my boundary curve. So this is the left hand side, so that's what I am written. The positive orientations relative to the orientations of my surfaces S. However, look at this picture. Instead of going in this direction, if I move in this direction, again normal pointing outward, that means it is towards in the directions of my head. But now look, if I move in these directions, in that case the surfaces is in the right hand side. So that means it is actually what is called negative orientations of the boundary curve. Okay. So that means the positive orientation means I have a smooth surface, I have some orientation, natural orientation is given to the surfaces. I want to move along the boundary of my surfaces in such a way so that the normal pointing upward, it should be in the directions of my head, and also if I go along in such a direction so that in the left hand side my surfaces will be there, then I will say that I will have a positive orientations of my boundary curve corresponding to the surfaces S or induced from the surfaces S. And if I go in such a directions on the boundary curve so that in the right hand side I will have the surface, then I will say that it will have a negative orientations in the boundary curve induced from the given oriented surface S. Okay. So I think it's clear the meaning of orientations. But well, by default case I will assume with a smooth surfaces which is positively oriented, and of course whenever I am talking about the positive orientations in the boundary curve, that means I am going in such a directions in the boundary curve so that my surface is in the left hand side and your normal pointing upward it is in the directions of my head. Okay. So by default I will consider that kind of things. Okay. Well, this is again clearly, so positive orientations of boundary curve of oriented surface. So it says that look, while walking along the boundary curve, the surfaces is on the left hand side. Look, I am going in this direction now. So that, and of course the corresponding normal at that point pointing towards in my directions of my head, right? And if I go in this direction, in the left hand side surfaces is there, so therefore left hand side, so therefore the directions of walking in the boundary curve is actually positive orientations of my boundary curve. So that means if I talk about positive orientations in my boundary curve, that means I should walk in the boundary in such a way so that in the left hand side I will have my surfaces. Of course, you have to be careful, the directions of the orientation of the surfaces, that means the unit normal should be in the directions of my head if I walk in this way. Okay. So that means the normal should be pointing towards my head and I should move in such a direction so that in the left hand side I will have my surfaces. If this is the case, then I will say that I am walking in a positive orientations along the boundary curve. See, one positive orientation boundary curve of oriented surface. This is another oriented surface. So at each point you have a normal pointing upward. So while walking along the boundary curve, the surfaces is on the left hand side. Why? Because look, this is the boundary curve now. So if I move in this directions, you see in the left hand side I have the surfaces. So therefore if I move in these directions, in directions of my head is normal is pointing upward, and if I move in these directions, in the left hand side I have my surfaces. So therefore this is actually I am talking about the positive orientations of my boundary. So that means the directions of walking is positive orientations of the boundary curve if I move in these directions. Okay. Default case, so that means that one, if I do not mention anything, so that means the default case is say that if S is oriented with the positive normal, that means I am starting with a smooth surface S, comma plus n cap, that means positive normals, and the boundary curve is or are oriented with the positive orientation. That means I should along through the boundary curve in such a way so that in the left hand side I will have my surfaces. So that means I am always talking about the surfaces with positive normals and in the boundary also positively oriented. So that means in the oriented positive orientation induced by the orientations of S. So that means you start with a surface, smooth surface with some orientation. Of course, that orientation I am talking about positive orientations, and also in the boundary I am by default case it should be always in the positive orientation. That means I should go along the boundary in such a way so that my surfaces should be always in the left hand side. That is the default case I will assume. Another way you can look at it, this positive orientations of the boundary curve of a given oriented surface, it says that what you do, so like you have to take it like say I have written the right hand thumb points the directions of the normal. So now you have a smooth surface. Suppose you start with a positive orientation, that means your normal pointing upward. Now what you do, if I take this is thumb, right hand thumb point rule kind of things. So if I put my thumb in the directions of the pointing the normal, that means this time I am starting with a surface, smooth surface S whose normal pointing upward. So in that directions if you put your thumb, then there should be a kind of, you see I have written, then the directions of the curling fingers determines the orientations of the boundary curve. So that means suppose I have a smooth surface which is positively oriented, that means the normal at the point direction is upward. So if I put my directions of thumb in that directions, so I will have this one kind of things. Okay, so I will have this one. So then you will have this kind of things. You look at the kind of directions of curling fingers that will determine the what is called orientations of the boundary curve. Look at the picture. So this is the kind of normal pointing upward. So look, this is my directions of thumb. So these two directions are same. So then looking at this kind of curly what is called fingers, what is the direction? So look, so I am actually, if I go like that, so I'll having this kind of direction. So that's exactly I have written. So in the kind of green one, blue one. So this is the one. So that means if I have a surface, smooth surface which is positively oriented, that means unit normal pointing upward, in that direction if I put my thumb, then the curly fingers determine the direction. What is the directions of these curly fingers? That means this is the direction. So that means this is the corresponding what is called positively orientations of my boundary. In other words, if I go in this direction, so that means this is the directions I am talking about, you see. So if I move in this direction, that means in the left hand side I have my surfaces, and that is actually positively oriented. So that means in this way you can also what is called get the what is called orientations of your what is called boundary curve. So that exactly I have written. So the right hand thumb points the directions of normals n cap, then the directions of the curling fingers determine the orientations of the boundary curve, which is called the positive orientation of the boundary curve. So that means there are two ways you can see. Either you can just start with a smooth surface with some positive orientations, and you should move along the boundary curve in such a way so that in the left hand side you will have what is called surfaces, then it is the positive orientations. Otherwise what you do, you just see, if you start with a smooth surface with some positive orientation, in the directions of the outward normal you put your thumb and look at the directions of the curling fingers, and that directions will give you the positive orientations of the boundary curve. So that's the two ways you can think about it. Okay. This is another one. This is the negative orientations of the boundary curve, the oriented surface. Look, this is the oriented surface. Now I have the kind of given the directions. So look, suppose this is my surfaces, right? So this is my surfaces. Now if I go in this directions, in this direction. Now if I go in this direction, you see in the right hand side I have my surfaces. Now, so that means of course this is the actually negative orientations of the boundary curve. So that's exactly I am written. So while walking along the boundary curve, surfaces is on the right hand side, because the directions I have given, this is the directions I have given. Okay. So if I go in this directions, my surface is in the right hand side. So therefore the directions of walking is the negative orientations of the boundary curve. In this case, the normals are minus n cap. That means that if I have a normal at the surfaces, it pointing inward, okay, or pointing, I should say, downward. These are negative orientations. Okay. So this is another example. So positive orientations of the boundary curve of oriented surface. Now this is a surface, but it has two holes actually. So this is one hole, this is another hole. So what kind of orientations in the boundary given some orientations of the surfaces? It says that is very nice. It says that the surface is oriented with two positive normals. So that means I have a smooth surface. Suppose you have started with some orientation with that surfaces, that means smooth surface, we say positively oriented, that means plus n cap, that means the unit normal pointing upward. That gives the positive orientations to the boundary curve C. Now look, this is the boundary curve, okay. So now this is positively oriented. Now if I move along in this directions, so in the left hand side I will have the surfaces. So therefore this orientations, that means given orientations of my surfaces which induce a positive orientations on my curve C, if I move along the curve in the anti-clockwise direction or counterclockwise directions. So that means given start with a smooth surface S with some with positive orientation, that means you have the normal pointing upward. Then if I move along the boundary curve, that means the curve I am talking about C, in the anti-clockwise directions or counterclockwise direction, that means my surfaces in the left hand side, that means I am talking about the what is called positive orientations of my boundary curve. Now you see, since the surfaces has two holes, so except C, I will have another two boundaries, that is C1 and C2. But this time what I have written, you see the positive orientations to the inner boundaries C1 and C2 of the holes as clockwise. That means in the inner hole C1, C2, if I move in the clockwise direction, that means my surfaces will stay in the left hand side, right. So this is my C1, this is my C2. Now if I move in the clockwise directions, my surfaces in the left hand side. Similarly, if I move in this direction, clockwise directions, that means my surfaces is in the left hand side. That means the orientations of my surfaces will induce a positive orientation. Positive orientation means what? That means I am starting with a smooth surfaces with some given orientation, and I should move along the boundary in such a way so that surface is always in the left hand side. If that is the case, then I will say that the orientations of the surfaces induce a positive orientations on the boundary curves. So in this boundary curve C, if I move along anti-clockwise or counterclockwise, that means my surface is in the left hand side, that means it will induce a positive orientation. However, these two boundary curves C1 and C2, I have to go in the clockwise directions, then only my surfaces will be in the left hand side and it will induce a positive orientation. So that's exactly I have written. So therefore, you start with the surfaces with holes C1 and C2, and if I have start with the surfaces with positive orientations, then that gives the positive orientations to the outer boundary. This is called the outer boundary C. If I move the counterclockwise or anti-clockwise directions, surfaces in the left hand side, then it will have the positive orientations, and in the inner boundary C1 and C2, if I move along the clockwise directions, then my surfaces will in the left hand side, and then it will have a what is called positive orientations. Okay, so that's another kind of examples. Okay. Okay, so I think I am in a position to talk about the statements of Stokes theorem. So now therefore it is clear that what is the meaning of surfaces, smooth surfaces, how to calculate normal, then what is the orientations, and how the oriented smooth surfaces induce a positive orientations in the boundary curves. Okay, so once I have those kind of concepts, then I am in a position to talk about the statement of Stokes theorem. What is Stokes theorem? Which is nothing but the three-dimensional versions of Green's theorem actually, and that is a tangential or curl form I will talk about. So Green's theorem I already discussed in my earlier lectures. So this is nothing but the three-dimensional versions of Green's theorem, which is known as the Stokes theorem. What is that? Let's see the statement. Okay, look. So Stokes theorem, this is three-dimensional version of Green's theorem. So suppose I have these surfaces, very nice surfaces, and with positive orientations of my surfaces, and of course it will induce orientations in the boundary curve, which is also positively oriented. That means I should move in these directions. So the surface is in the left hand side, or by thumb rule, if I put thumb in the outward directions of my normal, the directions will give you the orientations of my boundary curve. So that I already discussed. Now what is the statement? So look at the statement of Stokes theorem. It says that you start with a S, which is smooth surfaces, oriented positive normal. That means you start with S comma plus n cap. Okay. Assume that your surface is bounded by a closed piecewise smooth curve C. That means this is the piecewise smooth curve C. Okay, whose positive orientation is induced by the orientations of S. Okay, that means if you start, that means I am starting with a smooth surfaces with some positive orientations, and I want that this, or I should move along the boundary of my surfaces in such a way so that it induces a positive orientations of my boundary curve. That means I should move in such a way along the boundary so that my surfaces should be always in the left hand side. That means if this is my surfaces which is positively oriented, and if I move along these directions, this will be in the left hand side. That means this is the corresponding positively orientations in the boundary curve, or by thumb rule you can guess it. So once I have that surfaces S, then if I start with a vector field capital F, that means it's a map from R3 to R3 whose component is M, N and P, which is continuously differentiable. That means it's a very nice vector field I am talking about. That means the component continuously differentiable means what? It is differentiable and derivative should be continuous, right? So therefore, if I have a smooth surfaces with some orientation, given orientation or positively oriented, then it automatically, I am starting with of course it automatically induce orientations in the boundary curve, and I am talking about that it should induce the positive orientations of the boundary curve. Then you start with a vector field capital F, which is continuously differentiable on the vector field S. Then this is the corresponding statement. Then it says that the corresponding vector line integral of my capital F, that means integration over C f dr, which is same as integration over C m dx plus n dy plus p dz, that we have already observed, which is exactly equal to the surface integral of this object curl of f dot n cap, then over the S, right? So that is the relations between what is called the vector line integral over the curve C, that means in the boundary curve, which is exactly equal to the surface integral of the object curl of f dot product with n cap. So that means this is actually the scalar surface integral I am talking about. Okay, and the left hand side you have a what is called vector line integral, this because f dr. So this is the corresponding statement of Stokes theorem. Of course, this kind of statement you have seen in the context of, you see, Green's theorem. Green's theorem, if you remember, in the right hand side, instead of surface integral, it becomes a double integral. So if you start with a region, right? So in the boundary curve, the corresponding region, that means in two-dimensional picture, you will have the region, and there double integral was there. there, I think. Not I think, yes, it is the case actually, yes. So that time you have the integrations on the boundary, it actually same as the integral over the region R. Now in this case, in the Stokes theorem, I am talking about the Green's theorem, but in 3-dimensional. So there you will have, again, you have a start with the surfaces, look at the boundary, the corresponding vector line integral over the boundary, which is same as exactly equal to the surface integral of this object, curl of f dot n cap. That means this is the scalar surface integral. Okay, so this is the corresponding 3-dimensional versions of what is called Green's theorem. Okay, I think this is clear, the statement. So that means you start with a smooth oriented, say positively oriented surface, that means you have a positive normals, assume that S is bounded by a closed piecewise smooth curve C, whose positive orientation is induced from the given oriented surface S. And if I start with a vector field capital F, which is continuously differentiable on the vector field S, then the corresponding vector line integral of capital F is exactly equal to the what is called surface integral or integral of this object, curl of f dot n cap. Okay. So this is the corresponding Stokes theorem, which is you can interpret as a 3-dimensional versions of the Green's theorem. So let us see one example, then it will be much more clear. So look, I have written that verify Stokes theorem for this kind of vector field. That means you start with a vector field capital F of x, y, z, which is first component is 2z, second component is 3x, and third component is 5y, taking S to be the portions of the paraboloid. That means you have a paraboloid, you taking a portions of the paraboloid with normal pointing outward. So therefore, if I start with a surface S, which is a portions of the paraboloid, that means it is given z is equal to 4 minus x square minus y square, where z is positive, that means I am talking about the positive z axis with normal pointing outward. So I have to just verify, that means I have to just calculate the left hand side and right hand side, well, and see whether these two things are equal or not. Okay. Since my surface is the portions of my paraboloid z is equal to 4 minus x square minus y square, where z is positive, then first observation is that the boundary curve of this S is the circle, because if I put z is equal to 0, that means it is x square plus y square is equal to 4. That means in the projections, if I look at the projections of these surfaces in the xy plane, so it will give you the circle x square plus y square is equal to 4 in the xy plane with what directions? So I am starting with normal pointing outward, that means I am starting with a surface with positively oriented, and then the corresponding orientations in the boundary, which is also positively, right? So positive orientation I need it. So therefore in the xy plane with counterclockwise direction, that means I should move in the anticlockwise or counterclockwise direction, so that my surface is always in the left hand side, that means which is positive orientations induced by the given orientation of my surfaces S. Okay. So that is the first step. So that means first you see what surfaces I have given, then look at the boundary. That given oriented surface will have orientations in the boundary positively orientations. That means look at the corresponding boundary curve, and here in this example it is x square plus y square is equal to 4, and in this case what orientation I am talking about? I am talking about actually counterclockwise orientation. That means the positive orientation induced from the orientation given for the surfaces S, positively oriented, right? Then what you have to verify? So that means you have to just calculate what is the corresponding vector line integral over C, and then in the right hand side you just calculate curl of f and dot n cap, and then calculate the what is called surface integral, and you see you have to verify these two things are becomes equal. So okay, so first since the boundary curve is x square plus y square is equal to 4, then what is the corresponding parameterizations? You can easily write it. So my parameterizations is a circle, that means 2 cosine t, 2 sin t, and z component is 0. So that means this is the corresponding parameterization, t runs from 0 to 2 pi. So therefore the corresponding the left hand side, that means this left hand side, I am talking about integration vector line integral of capital F over C, which is nothing but integration C f dr, that you can write it, which is nothing but you see m dx plus n dy plus p dz, right? So what is my m n p? Here m is equal to 2z, n is equal to 3x, and z is equal to 5y. Of course, what is my capital F? So this is very nice. It is 2z, 3x, and 5y. Of course, this is very nice vector field. Each of the component functions are nice. It's a polynomial mean x comma y comma z, infinitely many times differentiable. So therefore it is a continuously differentiable vector field. So therefore it should satisfy the Stokes theorem. So let's calculate the left hand side, that means the vector line integral of capital F over C, which is nothing but this object, that means m dx plus n dy plus p dz. Just do that, the corresponding, just use the definitions of the line integral. That means if I just put it, that means this should be t from 0 to 2 pi, 0 plus, well, z is 0, so it will not, first one is not contribute anything. Second one is 3x, 3x means 3 times 2, 6 cosine t, 3x that means 6 cosine t, dy, y means 2 sine t, that means 2 cosine t dt, I mean this is, and what about the 5y dz, again z is 0, so it will not contribute, so only the second one will contribute. So this is the integral you will end up with, t from 0 to 2 pi, 12 cosine square t. If I do the what is called integrations, you will end up with the value will be 12 pi. So this is the left hand side you have verified. So look at the right hand side. So right hand side, since your vector field capital F is given, so you can easily calculate the curl of F. I am not doing it here actually, because your F is given, you know how to calculate the curl. So curl of F, there is a formula, that means I j k del x del y del z, and this vector field is there. If you calculate it, you will end up with the curl is nothing but this one. Also you can calculate your n cap. Okay, so curl, maybe you can use the formula, right? What is the curl of F? So your F is given now. So what is curl? So curl of F, which is nothing but, what is this? The determinant formula, I j k, then you have del del x, del del y, and del del z, and you have the vector field. That means 2z, 3x, and 5y. Okay. So you just calculate the perform this determinant. Okay. So it's very straightforward. So I'm not calculating it kind of in details, it's very straightforward to calculate. If you do that, you will have that curl of F is 5 I cap, 2 j cap plus 3 k cap. You please do that. So it is very straightforward to calculate it, and then you come to that what is called unit normal vector. How to do that? Because what is your surfaces? Surfaces z is equal to 4 minus x square minus y square, z is positive, right? So now if you remember, this is of the form z is equal to g of x y. That means explicit representation is given. Then you know what is the formula for what is called unit normal vector. What is the formula? So if I calculate, if I remember correctly, I think this should be minus gx I cap minus gy j cap and then 0. Okay, let me go back. Let me see. I think I have done it. Let me see. Yeah, you see, finding normal vector of the smooth surfaces which has explicit representation. Look, what is the formula? This one. See, minus gx I cap minus gy j cap plus k cap, right? So minus gx minus gy I cap j cap k cap, and this is square root of 1 plus gx square plus gy square. So minus gx minus gy. So minus gx minus g, calculate it, and it will be. So what is my g? Okay. So what is my g here? So look, this is my g na. So 4 minus x square minus y square. So my g of xy 4 minus x square minus y square. So what is minus gx? That is minus del g del x, right? What is that? So this should be minus 2x. Okay. And what is my minus gx? So that means minus of gx, that means it should be plus, right? Because already one minus sign is there. And what is minus gy? Minus del g del y. Again, this should be 2y, right? So what is the unit normal vector? That means if you remember, so minus gx minus gy, I think then plus k cap, right? Just forgot. Minus gx minus gy plus k cap, okay? So therefore, so what is the unit normal vector? So it should be have n cap, so minus gx I cap minus gy j cap plus k cap divided by square root of 1 plus gx square plus gy square, right? So you just do that. So minus gx, that means I have 2x 2y, and you have to have that square. Yes, that's fine, perfectly all right. So what is that? So this should be minus gx, that means this should be 2x I cap plus 2y j cap plus k cap square root of 1 plus gx square. Gx square means what? This should be 4x square plus 4y square, right? And what is that? 4x square plus 4y square. So this is x square plus y square is equal to 4. So that means gx is 2x, right? So 1 plus 4x square plus 4y square. So that means 2x I cap plus 2y j cap plus k cap. So I have 1 plus 4 times x square plus y square is equal to what? Plus y square is equal to 4. That should be a factor of something. That should be, it is not normalized. Okay, so let me just calculate it. Suppose assume that this is my unit normal. Maybe there is a constant factor is missing here. So the numerator is perfectly all right. 2x I cap plus 2y j cap plus k cap. So that the normalization factor is there, whether it is anyhow. So let me just see what is the statement. It is that positive normals, though I didn't say anything about what is called unit normal. Okay, so if I go ahead this one, so therefore just anyhow this portion I can take care in my next class. So there is a maybe some factor is missing, I'll take care of that part. Okay, let's see whether the left hand side and right hand side equal or not. So just calculate this surface integral. So you have the curl of f, you have the n cap, assume that this n cap is correct at the time. Okay, so you just perform it. So curl of f means this is the vector, and then n cap is this is the one. So this is a dot product, so that means it will give you this one, and you know surface integral how to calculate it. This is nothing but you just look at the corresponding parameterizations and you just look at the region and then you just perform this double integral. Okay, so if I do that, what is my region there? That means in the xy plane, the region, that means I am talking about the region bounded by my circle x square plus y square is equal to 1, then the circular region I am having. So if I have a circular region, that means what will be the corresponding parameterizations? R cosine theta, R sin theta, right? So therefore R from 0 to 2, because it is a circle x square plus y square is equal to 4, so therefore R from 0 to 2 and theta from 0 to 2 pi. In that region, it becomes that corresponding double integral, and if I perform it, then again you just do these calculations, you'll end up with this 12 of pi. So therefore this corresponding what is called the vector line integral of capital F over C, which is same as the corresponding surface integral. Okay, so I think this is verified for this example. My next lecture, I'll just confirm you whether this is the correct one or not. So okay, this is one example. I have another examples. Okay, what is that? Look, this is another example. So again, I will come back in my next lecture. I will come back with this observation so that this one is correct. I think some factor is missing. I think maybe I am missing some point here or not. Maybe next class I'll take care of that one. So let's go ahead with the example 2. So again, so find suppose this what is called surface integral over this surface S, where the integrand is curl of f dot n cap. Then what is my capital F? Capital F, this is kind of vector field, which is y square I cap x y j cap plus x z k cap. And what is my surface? S is the upper hemisphere, that means you have a sphere, upper hemisphere I am talking about. Okay, that means x square plus y square plus z square is equal to 1 in the upper plane with the unit normal pointing upward. Okay, then you know, so I have to calculate this object, right? So therefore by Stokes theorem, that means three-dimensional versions of Green's theorem, this surface integral is exactly equal to the corresponding what is called vector line integral of my vector field capital F over C. And what is my C here? In this case, my C is like x square plus y square is equal to 1 in the xy plane. So that means to calculate this one, you just calculate the corresponding scalar line integral of this vector field F. So okay, so that's exactly I have done. So where C is equal to x square plus y square is equal to 1, that means if I put z is equal to 0, if I see the projections in the xy plane, which is x square plus y square is equal to 1 in the xy plane. Again, I am talking about like my upper hemisphere in the what is called normal pointing outward, and it will induce a positive orientations in the boundary, and that means if I move along the counterclockwise and anticlockwise direction, my surface is in the left hand side, that means this is the corresponding positive orientation in the boundary. Then you can easily calculate the what is called scalar vector line integral. So using the polar coordinates, you just calculate this one, and this calculation you can easily do that. Why? Because you just perform it. X square plus y square is equal to 1, so you can have the parameterization. What is the parameterization? So that means if I just write it, say my r of t, which is cosine t comma sine t, right? And then t runs from 0 to 2 pi, that is the corresponding parameterizations, right? Then what is the formula? What is the formula of this one? If you remember, so this is 0 to 2 pi, capital F of r t, then r prime of t dt, that you have to perform. Okay, and what is that? This is 0 to 2 pi, capital F of r t. So that means what is my capital F here? Okay, you can calculate it. So capital F of x comma y comma z, which is y square comma xy comma xz, right? This is my capital F. RT, okay, RT I think I should put the component should be 0, right? Z component, yes. So this is the corresponding parameterizations of my C. Then what will be that? So therefore this is my capital F and this is my RT. So therefore first what is my R prime of t? R prime of t is nothing but minus sine t comma cosine t comma 0. This is R prime t, and then you just see f of RT. F of RT, that means it will be there like RT, right? So this means y square. Y square means that means first one is sine square t. Then x times y, that means you have sine t cosine t. Then z is 0, so it will not contribute anything, comma 0, dot product with what? Minus sine t comma cosine t comma 0, then dt. Okay, you have to calculate this one. And what is that? So if I do that one, so that means it will nothing but 0 to 2 pi. What will happen? So you will have sine q t minus sine plus sine t cos square t dt, right? You will end up with this one. and again do some calculations here. So, then 0 to 2 pi, if I take sin t common, it should be cos square t minus sin square t dt, and what is that? Again 0 to 2 pi, this is sin t, and cos square t minus sin square t, if you, I think this should be cosine of 2t, if you remember, I think this should be the case. You just look at the trigonometric formula. Okay. So, that means what I want, that means I have to integrate this object sin t cosine of 2t from 0 to 2 pi. Again use that what is called sin, some formula, sin a cosine b, sin of a plus b by 2 plus I think cosine of or sin of a minus b by 2, this kind of formula. I am not doing it fully, but the point is that if I use some trigonometric formula, you will have the combination of sin plus cos or sine, but at the end of the day I am integrating over the full circle 0 to 2 pi. So, it will give you the 0 value. Okay. So, these calculations roughly I have done it. So, up to this part is perfectly all right, 0 to 2 pi sin t times cosine of 2t, then you just use some trigonometric formula. You can break up into two parts in terms of either sine cosine or sine or cosine, whatever it is, some formula is there. So, but at the end of the day you have to do 0 to 2 pi some sine plus 0 to 2 pi some sine or cosine, but anyway I am integrating on the full circle 0 to 2 pi. So, therefore, integration will always be 0. So, therefore, in the right hand side if I perform this what is called vector line integral, it will give you 0. So, therefore, this object by Stokes theorem, which is nothing but this vector line integral of my vector field capital A, which I can easily calculate, this is 0. So, therefore, the corresponding surface integral is 0. So, that is another examples of what is called applications of Stokes theorem. Okay. Okay, so I think I should stop here. In my next class, I will start with the version of Stokes theorem where you have a surfaces, but you might have some holes in the inside the surfaces. So, earlier one I have a just nice surfaces, there is no hole in that surfaces. Then I have a statement of my Stokes theorem, examples I have talked about, couple of examples. Now, next class I will start with the statement of a Stokes theorem with some surfaces that has some holes, like in the Green's theorem I did it, right. So, I simply connected I start with, then I have stated the Green's theorem for a multiply connected region, right. So, that means there are some holes in the region. Similarly, in this statement of Stokes theorem, first I started with the Stokes theorem with some nice surfaces, some oriented surfaces, there is no hole, right. But now I will kind of give the statement of Stokes theorem. I will start with a oriented surface which has some holes. Okay. So, then see the parallelly like in the statement of Green's theorem in the two dimensional versions, it will be similar kind of things will also be there in the statement of Stokes theorem if I start with a surfaces oriented surfaces which has some holes. I think I should stop here, but I will come back to this example whether this is unified or not. So, I will come back in my next lecture. I think I should stop here. In my next class I will start with the statement of Stokes theorem if I start with a surfaces with some holes, and then I will talk about the statement of divergence theorem. I think I should stop here. Thank you.